here is an angular momentum question for you. So I gave this in my astrophysics class, and it led to a great discussion, even though that we didn't finish. So I'm gonna answer this question and then ask a better question. So the question is that we have this ball moving in a vertical circle at a constant speed. So it's just going around and around, which right there tells you it couldn't be on a string. It wouldn't move in a constant speed. Okay, but it's moving in a constant velocity around in a circle, and the question is what happens to the vector value of the angular momentum about point A, which is the center, as it moves around there. And remember, if you want a little hint, the angular momentum L for a point mass is R cross P. So maybe that tells you the answer right there, but I'm going to go ahead and tell you the angular momentum is constant about point A, because at any particular point, there's my vector R, there's my vector P. So R cross P using the right-hand rule would be this way, right? R cross P. And we can find the magnitude of L as RP sine theta, but theta is 90 degrees right there. So that's one thing. If I move over here, then I still have R is that way, P is that way, R cross P is still this way, and the magnitude's the same, the angle is the same, everything's the same. So it doesn't really matter where it is. And maybe that's not a surprise to you, but the next question is going to be better. But before I do the next question, what I want to do is to model this in WebVPython so we can see what it looks like, we can calculate, we don't have to verify it, we can just do it. Now, the first thing is, how do you make an object move in a circle? Well, here's what I'm going to do. I'm going to start with a new circle. Here's my circle. I have this point in the middle, I'll call it PA, and I have my mass over here. If I have a force that's always perpendicular to the velocity, then it will move in a circle. Now the question is, what's the relationship between the force and the velocity? We have to calculate that. So let's make everything easy. Here I have a circle of radius 1, and I'm going to have a mass of 1. And I want to let's say I have a force, the magnitude is 1 newtons. So everything's 1. What would the velocity be? So in this situation right here, I can say that F net in the R direction is going to be equal to, let's call this F0. F0, right, negative F0, and that's going to be equal to negative m times the acceleration, but it's the acceleration of an object moving in a circle, v squared over r. So if I solve for v, I get v equals the square root of f r over m, but all those things were 1. See, I was thinking right. So v is 1. 1, 1, 1, 1, 1. 1's everywhere. Now, how do we actually do this in Python? Well, in Python, what we're going to do is to describe this vector. We're going to have a ball, and it's going to have a position vector. And then I'm going to call this ball 1, and I'm going to call this vector r1, which is the position, but that's fine. And then I'm going to write the force F as negative F0 R1 hat, right? So now as the ball moves, the direction of the force changes too. So, but the magnitude stays the same. And let's see if it moves in a circle. And then we can try different things. Okay, so you could make this like a spring. You could do other forces to make it move in a circle, but this one's the easiest. And let's just do easy. Jumping to WebVPython. Okay, so here we are. Make this bigger. I'm going to take off my glasses because I can just see a little bit better. Make that bigger, bigger, bigger. Okay, is that too big? I don't know. So let's just put our constants in here. I'm just going to use a constant of m equals 1. I don't know if I should do that. R equals 1. F0 equals 1. And then v is the square root of, what did I say right there? F times R divided by m, which I already knew. Okay, so no surprise there. Now I'm going to put a point in the middle. I'm going to call it PA. PA is equal to a sphere. The position is vector 0, 0, 0. And then I'm going to give it a radius of, let's say, R over 20. And then ball 1 is going to be a sphere. Position is going to be, I'm going to start it on the x-axis. Position is vector R, 0, 0. And then let's make this one a little bit bigger. Radius equals R divided by 15. Color is color.yellow. Make trail equals true. Okay, let's just run that and see if things are working so far. See, good thing you ran it, huh? Can't find f because I'm dumb. F is 0. Okay, looks good. Now I'm going to pick my time. Now I do want to set my momentum of my ball, and I'm going to go ahead and do that. Ball1.m equals m. I'm going to do it that way. And then ball1.p is going to be ball1.m times vector 0 v 0, right? Because I want it, if it's in the x-axis, on the x-axis, I want it to be moving up in the y direction. T is 0, dt is 0.01, while t is less than, let's say, 7. I don't know why I picked 7, I just did. Can't see that. Rate 100. Now what I'm going to do is to calculate the force. To do that, I'm going to have the vector r1. r1 is going to be ball1.pos minus the location of PA, which is the origin, PA.pos. And you could just use ball1 right here, but .pos, but I'm not going to. F is going to be equal to negative f0 times the norm of r1. So remember, norm is a unit vector in the direction of r1, so that's good. Now I can use that to update the momentum. I skipped over the whole numerical calculation thing. I think you've seen that a bunch of times. If you haven't, comment down below, and I will give you the best link to show you how to do a numerical calculation in Python. Okay. Ball1.p, ball1.p plus f times dt. Now I update the position. Ball.pos, p-o-o-s, ball1.pos, ball1.p times dt divided by ball1.m. T is t plus dt. Let's run it. And it didn't do anything. Can't find ball. Ball 1. Okay, so it's moving in a circle, and I think that's great. And now I want to point out, you could make things move in circles other ways, right? I could just say, what's the theta value, and calculate x and y, and just change my theta value with some angular velocity and move around in a circle. But I want to calculate the angular momentum, so I need that p vector. I need the momentum. So this way I'm updating the momentum anyway, and I can calculate that. Okay, now what I want to do is to plot the angular momentum as a function of time, the z component of the angular momentum. So let's do that. I should save this. Save. And up here I'm going to make a graph. G1 equals graph. And let's just say x title equals t. And then y title equals LZ. And then width 400, height 200. And I'm going to have a couple graphs. So let's just start off with F1. That's the angular momentum of ball 1. F1 equals G curve, color equals color.blue. And I'm going to put a label here, even though we don't need it for now. Label equals ball 1. Now, I want to calculate the angular momentum. We could display it as a vector too, but I'm just going to calculate if you want to know how to do the vectors, I'll show you, but let me know. But otherwise, I'm not going to do that. So down here, I'm going to calculate the angular momentum. So L1 is going to be the cross product of R1 and ball1.p. So that's pretty easy to do. Now I can just plot that, the z component. I know it's in the z direction. F1.plot t L1.z. Let's run it. And you see that it's not constant. We said it would be constant, but it is constant. Gotcha. Okay, let me look at this. 1.0000004, 1.0000002. So I mean, it's just fluctuating. It looks fluctuation, just a rounding error. It's not a big deal. That's constant. Okay. Now, let's look at our next question, the fun one. Here we go. Glasses back on, switching to overhead. Suppose that I now want to calculate the angular momentum about this point. So this is r and a half. So this is 1.5 r below that, and then we'll call that point B. So if I switch my point about which I calculate the angular momentum, what would happen? Would it still be constant or would it change? What do you think? Well, let's just look at a couple cases. I'm going to put it over here. I don't know why I'm moving over there. Or even right here. So imagine this is R, and this is moving this way. Up here is moving that way, and that's my R. So they're still 90 degrees apart, but now the R values are not the same, and the direction's not the same, right? This one has an angular momentum this way, that one has an angular momentum that way, so it changes both magnitude and direction. Let's just plot it and see what happens, okay? Switch back to Python, and let's add a second point. So I had PA, let's add P2. Oops, that was messed up. PB. PB, it's a sphere. Its position is going to be vector 0, negative 1.5 times R0. So it's below the thing, but it's going to have the same radius. Radius is R over 20. Now, I want to calculate the vector from that point to the new object. So let's just change this R1. I'm going to change this to PB.pos, right? That's all I need to do. And other than that, no, that's not going to work because that uses R1. So let's change that back to A. Let's call that just R. Let's call this ball1 dot. No, let's leave it as R1. R1, let's call that R1A. And then R1B is going to be ball1.pos minus PB.pos. And down here, I'm going to calculate the angular momentum as R1B cross that. And let's see, this has to be A, and then it should work. Okay. So right there, you see non-constant angular momentum. It's going up, it's going back down. I said it would change direction. Let's see if it actually does change direction, which means negative z component, and there you got a negative z component. So the angular momentum is not constant. And it seemed kind of weird. Doesn't it seem kind of weird? Like, I didn't do anything. The object's still moving with the same force and the same everything. So why is the angular momentum not constant? Let's go back to the board for a second. And look at this example right here. So I have this ball, and there's a force pulling it that way. If I also use the angular momentum principle, this says that the net torque about, let's say, point B down here, about point B is dl dt. That's the angular momentum principle. So if the net torque is 0, the angular momentum would be constant. Okay. So, but here the torque is not 0. You can see right here that that ball, there's a force exerting, well, in that case, the force is this way exerting a torque. But right here, the force is that way, and R is that way. That's a torque, right? Remember, torque is R cross F, about point B. So there's a torque that way, there's a torque when it's right there, and it's a different torque. So the torque is not 0, and the torque is not constant. Now, however, if I switch to the point A system, the force is always pointing toward the center, and there's no torque. Okay, so that's why. But then that doesn't seem fair, right? It doesn't seem fair. Well, it's not fair because we can fix this whole situation, and we can make the net torque 0 if we include both points. So if I have a force F exerted on this mass, then I let that mass move too, then we can get no torque, right? If I have equal and opposite forces on these two masses, the total torque is going to be 0. Now, let's do the following. I'm going to have PA, I'm going to let it move. I'm going to give it a large mass, let's say 20 kilograms. So it's kind of not really moving, but it'll move a little bit, right? So as this thing moves around, that point's going to move too. And then we can recalculate the angular momentum at the center for point A, and then we'll do it for point B, and we'll see that it's constant. So I actually want to plot the angular momentum for ball 1, the angular momentum for PA, and then the total angular momentum. And then I'll repeat it for down here. That's what we're going to do. So let's go back up here, and I need to change. You notice I already made that an object, PA. Let's give it a trail. Make because it's going to move, trail equals true. I'm going to give it a mass. PA.m is going to be 20. So it's 20 times as much, which is a lot. Maybe too much. Now down here, I need to also give it an initial momentum. If I'm going to update its momentum, I need to start with the momentum. In order to make the whole system at rest, I'm going to say that PA.P is negative ball1.P, right? So now the total momentum is 0, and that'll be good. I'm not going to calculate anything. I just want to model this motion. So right here, I'm updating the momentum of ball 1. I need to do the same thing for PA. PA.P is going to be PA.P minus F times dt, right? Because I calculated that force on ball 1. There's an equal and opposite force on PA. And then I need to update its position. PA.POS, PA.POS plus PA.P times dt divided by PA.M. Okay, so now let's just think for a second. This R1A, so you notice that PA moves, right? So R1A is not a constant value. It's going to change. It could even change magnitude and everything. And this, we're not going to use that one right there. So that force isn't always pointing straight towards the center, towards the origin, because A moves. Okay, so now we're going to calculate the angular momentum with respect to the origin, which is the vector 0, 0. So I do need to change this stuff. So this R1B is actually going to be just ball1.POS, which is different than R1A, right? Because, like I said, point A moves. And now let's go up here and make 2 more graphs. I'm going to make F2 as a G-curve, color.red, label equals PA. And then I'm going to say FT is G-curve, color.purple. You got to pick your colors, because if you pick something that's too dark, it doesn't show up, or too light doesn't show up. And this is going to have a label, just total. So down here, I'm going to plot, I need to calculate L. I'm going to call it LA. LA is going to be the cross product of PA.POS and PA.P, R cross P, same thing. And then I can just plot the total. Let's just calculate the total. LT tot is going to be L1 plus LA. Now let's plot these. That one's fine. F2 dot plot TL. Why did I call it 2? A dot Z, and then FT dot plot TL tot dot Z. Let's see what kind of damage we did here and if this actually runs. No. Can't find ball. I did it again. Why did I do it again? Ball. Where did I do ball? It must be somewhere down here. Did it right there. Okay, do you see that little ball moving? See that? It's making a little circle. So they're both moving, but it is moving in a circle, okay? They're both moving in circles. And then there's my total momentum. So my total momentum is constant. Ball 1 does change, right? And ball 2 does change in the opposite direction. But the total momentum, angular momentum, is constant for the system. Now let's just switch it down to the bottom mass. Just for fun, show that it has a total of 0 also, or constant, I'm sorry. I'm not going to, PB is just a location. It's not a mass that's moving, right? The force is between PA and ball 1, which my labeling is kind of silly here. So I really just need to go down here and worry about the calculations. So to calculate L1, I need to find the vector from PB to ball 1. So let's call that R1B, which I had up there, and I already did that. But now I need to calculate the momentum, the R for RA. So RAB is going to be PA.POS minus pb.pos. So that's the vector from pb to pa. And then down here when I calculate RA, see this is fine, I just need to change this to R1A. And then this is going to be equal to RAB. But other than that, it should be fine. The motion's the same. And now you see here, oh, the total is not the same. What did I do wrong? Now ball one has constant. Oh, that's why. Because that was for B. Duh. Wow, I found something out awesome. But this is supposed to be B. Sorry. There. Constant angular momentum right there. But the two angular momentums of ball A and PA do change. They add up to a constant momentum. Angular momentum is conserved if both the objects can move. So I just want you to know how this relates to astrophysics, because we're going to do things like an object orbiting the sun. You'll notice it doesn't quite meet up right there. That's just because of a rounding error. You can't even see that. So if you look at like an object orbiting the sun moves too. So if you don't include the angular momentum of the sun as the object orbits it, then you can get a non-constant angular momentum. But really the angular momentum should be constant for the system. Okay, so the code for this down below. Again, if you want me to go over different parts of the calculation, just let me know. I'll be happy to do that and make another video. But that's that for now. Talk to you later. The end.